In crystallography, the cubic crystal system is a crystal system where the unit cell is in the shape of a cube. This is one of the most common and simplest shapes found in crystals and minerals. There are three main varieties of these crystals: primitive cubic, body-centered cubic, face-centered cubic. Each is subdivided into other variants listed below. Note that although the unit cell in these crystals is conventionally taken to be a cube, the primitive unit cell often is not. This is related to the fact that in most cubic crystal systems, there is more than one atom per cubic unit cell. A classic isometric crystal has square or pentagonal faces. Cubic space groups. The three Bravais lattices which form cubic crystal systems are: the primitive cubic system consists of one lattice point on each corner of the cube. Each atom at a lattice point is then shared equally between 8 adjacent cubes, and the unit cell therefore contains in total one atom. The body-centered cubic system has one lattice point in the center of the unit cell in addition to the 8 corner points. It has a net total of 2 lattice points per unit cell. The face-centered cubic system has lattice points on the faces of the cube, that each gives exactly 1/2 contribution, in addition to the corner lattice points, giving a total of 4 lattice points per unit cell. Each sphere in an FCC lattice has coordination number 12. The face-centered cubic system is closely related to the hexagonal close-packed system, and the two systems differ only in the relative placements of their hexagonal layers. The 111 plane of a face-centered cubic system is a hexagonal grid. Attempting to create a C-centered cubic crystal system would result in a simple tetragonal Bravais lattice. Crystal classes. The isometric crystal system class names. Examples: Schonflies notation, Hermann-Mogan notation, point groups. International tables for crystallography. Space group number, orbifold type, and space groups are listed in the table below. There are a total 36 cubic space groups. Other terms for hexoctahedral are: normal class, holohedral, detesseral central class, galena type. Voids in the unit cell. A simple cubic unit cell has a single cubic void in the center. A body-centered cubic unit cell has 6 octahedral voids located at the center of each face of the unit cell, for a total of 3 net octahedral voids. Additionally, there are 36 tetrahedral voids located in an octahedral spacing around each octahedral void, for a total of 18 net tetrahedral voids. These tetrahedral voids are not local maxima and are not technically voids, but they do occasionally appear in multi-atom unit cells. A face-centered cubic unit cell has 8 tetrahedral voids located slightly towards the center from each corner of the unit cell, for a total of 8 net tetrahedral voids. Additionally, there are 12 octahedral voids located at the center of edge of the unit cell as well as 1 octahedral hole in the very center, for a total of 4 net octahedral voids. One important characteristic of a crystalline structure is its atomic packing factor. This is calculated by assuming that all the atoms are identical spheres, with a radius large enough that each sphere abuts the next. The atomic packing factor is the proportion of space filled by these spheres. Assuming 1 atom per lattice point, in a primitive cubic lattice with cube side length A, the sphere radius would be A2 and the atomic packing factor turns out to be about 0.524. Similarly, in a BCC lattice, the atomic packing factor is 0.680, and in FCC it is 0.740. The FCC value is the highest theoretically possible value for any lattice, although there are other lattices which also achieve the same value, such as hexagonal close-packed and one version of tetrahedral BCC. As a rule, since atoms in a solid attract each other, the more tightly packed arrangements of atoms tend to be more common. Accordingly, the primitive cubic structure, with especially low atomic packing factor, is rare in nature, but is found in polonium. The BCC and FCC, with their higher densities, are both quite common in nature. Examples of BCC include iron, chromium, tungsten, and niobium. Examples of FCC include aluminium, copper, gold, and silver. Multi-element compounds. Compounds that consist of more than one element often have crystal structures based on a cubic crystal system. Some of the more common ones are listed here. Cesium chloride structure. The space group of the cesium chloride structure is called PM3 or 221. The structure Beric's designation is B2. One structure is the interpenetrating primitive cubic structure, also called the cesium chloride structure. Each of the two atom types forms a separate primitive cubic lattice, with an atom of one type at the center of each cube of the other type. Altogether, the arrangement of atoms is the same as body-centered cubic, but with alternating types of atoms at the different lattice sites. Alternately, one could view this lattice as a simple cubic structure with a secondary atom in its cubic void. In addition to cesium chloride itself, the structure also appears in certain other alkali halides when prepared at low temperatures or high pressures. Generally, this structure is more likely to be formed from two elements whose ions are of roughly the same size. The coordination number of each atom in the structure is 8. The central cation is coordinated to 8 anions on the corners of a cube as shown, and similarly, the central anion is coordinated to 8 cations on the corners of a cube. Other compounds showing cesium chloride-like structure are CSBr, CSA, high-temp RBCl, Alco, AgZn, BeCu, MgCe, Rul, SRTL. Rock salt structure. The space group of the rock salt structure is called FM3 or 225. The structure Beric's designation is B1. In the rock salt or sodium chloride structure, each of the two atom types forms a separate face-centered cubic lattice, with the two lattices interpenetrating so as to form a 3D checkerboard pattern. Alternately, one could view this structure as a face-centered cubic structure with secondary atoms in its octahedral holes. Examples of compounds with this structure include sodium chloride itself, along with almost all other alkali halides, and many divalent metal oxides, sulfides, selenides, and tellurides. More generally, this structure is more likely to be formed if the cation is somewhat smaller than the anion. The coordination number of each atom in this structure is 6. Each cation is coordinated to 6 anions at the vertices of an octahedron, and similarly, each anion is coordinated to 6 cations at the vertices of an octahedron. The interatomic distance in some rock salt structure crystals are 2.3 A for NaF, 2.8 A for NaCl, and 3.2 A for SNTe. Other compounds showing rock salt-like structure are LiF, LiCl, LiBr, LiI, NaF, NaBr, Ni, Kf, KCl, KBr, Ki, RBF, RBCl, RBBr, RBI, CSF, MgO, PBS. AgF, AgCl, AgBr. Zinc Bleywender structure. The space group of the zinc Bleywender structure is called F43 or 216. The structure Beric's designation is B3. Another common structure is the zinc Bleywender structure, named after the mineral zinc Bleywender, one form of zinc sulfide. As in the rock salt structure, the two atom types form two interpenetrating face-centered cubic lattices. However, it differs from rock salt structure in how the two lattices are positioned relative to one another. The zinc blender structure has tetrahedral coordination. Each atom's nearest neighbors consist of 4 atoms of the opposite type, positioned like the 4 vertices of a regular tetrahedron. Altogether, the arrangement of atoms in zinc blender structure is the same as diamond cubic structure, but with alternating types of atoms at the different lattice sites. Examples of compounds with this structure include zinc blender itself, lead nitrate, many compound semiconductors, and a wide array of other binary compounds. Other compounds showing zinc blend-like structure are alpha-AgI, beta-BN, CuBr, beta-CDs, BP-bar Werfelland structure. The Werfelland structure has PM3N symmetry. It has three orientations of stacked tetradecahedrons with pyritohedral cells in the gaps. It is found as a crystal structure in chemistry where it is usually known as the type 1 clathrate structure. Gas hydrates formed by methane, propane, and carbon dioxide at low temperatures have a structure in which water molecules lie at the nodes of the Werfelland structure and are hydrogen bonded together, and the larger gas molecules are trapped in the polyhedral cages.